choose to go to the moon in this decade and do the other things.
It's one small step for man, one giant leap for mankind.
All right, come on back. There's more to show you.
Not because they are easy.
Firefly Aerospace's robotic spacecraft touching down on the moon.
Live TV interview with the crew of Artemis 2.
But because they are hard.
For decades, humanity has dreamed of a future among the stars. But survival beyond Earth isn't just about reaching new worlds, it's about thriving in them. On the moon, water is the currency of survival, and the key to unlocking its potential lies buried beneath the surface.
The challenge is simple in concept, but complex in execution. How do we extract water from the lunar surface in a way that's efficient, reliable, and adaptable to future lunar missions?
Deposits of ice can be found within the regolith of permanently shadowed regions at the moon's poles. Untouched by sunlight, these areas can reach temperatures as low as -250 degrees Fahrenheit. If the US has any hope of establishing a permanent lunar base in the future, gaining reliable access to water like this is key. A team based out of the University of Arizona is focused on creating a proof-of-concept system that will collect icy regolith simulant and extract water from it. For the past 6 months, they have been designing and building their system in a laboratory in the Mines and Metallurgy building.
For this challenge, our team decided to use a 2-unit system. The Mobile Excavation Unit, or MEU, extracts icy lunar regolith from the lunar surface using a bucket elevator subsystem. From there, it transports the regolith to the SEU, or Stationary Extraction Unit. There, the regolith is moved into a heating chamber where the water is first melted and then evaporated out of it. The water then passes through a shell and tube heat exchanger to condense it back to liquid water for use. For this project, we had both a limited timeline and a limited budget, so we had to make sure that we made every design decision count.
Rachel is the team's procurement lead and mechanical engineer. Today, she is building a frame for the Stationary Extraction Unit, or SEU.
So today we're cutting some of the framing for the SEU's frame. Right now we're cutting the 3-foot-long legs, so we're using the metal saw here at the EDC.
As the team conducted research for this project, they looked to the past, studying the achievements of previous lunar missions, and to the future, exploring the advancements shaping space exploration today. These efforts were led by research lead, Ellie.
The Apollo missions of the 60s and 70s used rovers very similar to what we plan to build, so they're a great place to start with research.
With mesh wheels, solid axle suspension, and lightweight aluminum frames, the designs of the early Apollo missions are perfectly adapted to the lunar surface. But right now, the team is focused on creating a proof-of-concept design, meaning it will operate under Earth environmental conditions.
Lunar materials are very expensive, and that leads to long lead times in procuring components, and a lot more difficult of design decisions to be made. In order to demonstrate that the system works in the first place, as conceptualized, a proof of concept allows us to test under Earth conditions using more available material and resources.
But just because this project is a proof of concept, doesn't mean it's without requirements.
Our system will extract water from the icy regolith over a 24-hour period. This means the ability to traverse and dig deep enough is extremely important. The bucket elevator system will be capable of excavating 10 to 20 centimeters deep.
With so many moving parts, how do they know everything is working as it should? That's where mathematical models come into play. Using math, the team can precisely determine the system's inputs, outputs, and overall capacity long before a single piece is built.
Based on the 3.42-liter volume of the heating chamber, and assuming that it's filled up to 3 liters per cycle, as well as considering that the regolith is 5% water by weight, we could find the number of cycles needed to hit our requirement of ½ liter per day.
These models go beyond mathematical equations. As team lead, Emerson's job is to keep the project on schedule and under budget. He's also taken on the task of developing 3D models for the Mobile Extraction Unit, or MEU.
Today I'm working on fitting out the 3D printed parts for our mobile excavation unit. To do that, I'm looking at what I put in my design in SolidWorks, grabbing the hardware we bought, and threading it in to make sure everything fits up as expected. Right now you can see the bucket elevator frame, the slide mounts here, the slide rails here. Both motors are a fit onto the chassis. The next piece I'm going to fit up will be the motor cover.
But none of this is possible without the proper electronics and software. That's where electrical engineer Alex comes in.
Alright, so in order to power the MEU, we're going to use a 24-volt battery. It's going to be going to the common connection of a relay.
Alex is working closely with Chad, who has years of experience developing robotics for the moon.
The microcontroller will be using a separate battery that will be non-rechargeable, and that way we can keep all of the essential components on.
While the SEU may lack electrical components unlike the MEU, it is no less complex.
It starts off with a funnel at the top where regolith enters from our mobile unit. From there, the regolith passes through this open ball valve right here into the heating chamber, which is this large pipe in the center here. There's another ball valve at the bottom to control flow in and out of the chamber for the dehydrated regolith.
But how will the team verify that these multifaceted systems work as they should?
For this project, we've accessed the San Javier Mining Lab, which is a really sandy landscape that mimics the surface of the moon. We've been able to confirm that our system works and that our MEU can excavate to a maximum depth of 10 centimeters, while our SEU can extract a minimum of half a liter of water in a 24-hour period, meaning that our system hits all of our major requirements.
Located just south of Tucson in Sahuarita, San Javier is one of the few student-run underground mining facilities in the world, making this undergraduate lunar project all the more special. But with researchers across the country pursuing efforts similar to these, what else sets the Larp team apart?
Previous work has demonstrated the ability to excavate regolith from the moon, but we're taking that a step further. Our project also has a plan for how to extract water from that regolith. Working with people from so many different backgrounds, from aerospace and mechanical engineering to systems and electrical, has also really given us an edge because we have so many different perspectives to go off of.
From a classroom on Earth to the dream of a lunar outpost, Larp is just one small step toward the giant leap still to come.
This project has taught us about more than just engineering. It's about preparing for a future where we help humanity thrive, whether that's on Earth or one day the moon. So come see us on Design Day.
What we're doing today?
No idea.
The lunars. Crap.
PLC's coming on.
It's recording, but take your.
Oh, okay.
Right now, this instant, Alex just walked to his car.
Oh no, I don't think I hit the record button. It's not like there's much to record anyways.
There's some number of people in this other room.
That's stupid.
That's all I have for you right now.